G'day everyone, my name is Bruce Koo, and I will be the presenter to present our paper, Dual Scheme Privacy Preserving Approach for Location-Aware Application in Edge Computing. So in this presentation, we will split in 5 major sections. We'll introduce the background first, then introduce the formulation of the adversary attack, and then we will discuss the system modeling and analysis, and then we will evaluate our experiments. At the end, we will conclude the presentation and present with some future works. So first of all, we'll introduce a little bit background about this paper. So the Internet of Things is basically advancing at a breakneck pace, and the connection between things is becoming more pervasive. So increasingly more objects are becoming intelligent as they are capable for seeing their surroundings, connecting to the internet, and receiving instructions remotely. So these intelligence of the objects are derived from data analysis and input from a variety of the systems or servers connected to a variety of the mobile devices. So the wireless and the decentralized properties of edge nodes are vulnerable to adversaries in actual application process of edge computing, resulting in a major location-aware privacy disclosure vulnerabilities. Edge computing enables the computation to take place closer to the user, and it will evaluate the data locally and make decisions based on it. It decreases the danger of privacy leakage by avoiding long-distance data transfer in the network to certain content. However, a substantial amount of the sensitive private data can be retrieved since attackers can easily access real-time data received by the edge nodes. So higher criteria for privacy-preserving protection techniques in edge computing have been recommended as a result of methodologies that assure user can utilize the service without revealing their sensitive location data. Traditional privacy preserving solutions are impractical for directly addressing the highlighted problems in an effective manner, and despite certain existing privacy preserving models or algorithms being presented. And furthermore, the location privacy disclosure concern identified in the edge computing will have a significant impact on edge computing application development. It is critical to investigate location-aware privacy protection solutions for large-scale edge computing applications based on location. So therefore, motivated by this, in order to achieve an optimal trade-off with high accuracy and efficiency on data utilities, we offer a dynamical dual-scheme Epsilon customized differential privacy model. We named that as a DDSDP, and that was based on a software-defined edge computing service. The software-defined edge computing increased the network's privacy protection capabilities by allowing it to be programmed with flexibility and a dynamical. So our contribution for this paper are summarized in 3 major points. So first of all, we offer a dual-scheme Epsilon customized differential privacy model to retain a location-aware private data for users. And in addition to that, to offer first-scheme protection for location-aware data from user to edge nodes, we consider a dynamic clustering strategy. So these will protect against frontal attacks from adaptable faults. So furthermore, we adopt affinity propagation methods to boost the efficiency of the clustering approach while retaining the greatest degree of privacy protection level. And then secondly, we designed our second approach as an Epsilon customized protection method with a modified Laplacian mechanism by providing noise to the clustered edge node. We developed a quality of service-based tool to map the distance between privacy protection levels. And our model DDSDP that seeks to enhance data utility while minimizing privacy costs. And to illustrate the proposed models, we performed extensive experiment on the real-world dataset. The evaluation results reveal notable significant performance in terms of data utility and a privacy protection level. Then the second part of today, we will introduce the formulation of adversary attacks. The volumes of information that attacks may extract from a user location privacy data after it is broadcast influences the effectiveness of the adversary attack model of a location-aware privacy in edge computing. The location data captured by the adversary's front user can encapsulated in a set of spatial data. And adversaries can easily deduce users' privacy information based on location data by predicting the probabilities. We named that as a P. When user is in a sensitive location at a particular time. So we define the location data by providing the user at any moment where it does not disclose the data, the theta data privacy of a user at a sensitive place to qualify the location data collected by the adversary in order to infer the user at a given sensitive location. We define the location data that user published at any specific moment, and that particular moment does not disclose the theta privacy of user in a sensitive location in order to evaluate the adversary's location data collection and deduce the user in a particular sensitive area. So therefore, we promote our first definition, which is named as location-aware privacy. So in that particular equation, we define that in any time t, to present the probabilities rate for the user at the location S, I, and meeting the time of t, and we use PUIT. We also use the LDT to define the location data collected by the attackers at a particular time t. So as a result, we have our first equation. So we're in that equation where the theta denotes the user privacy requirements, and then the first half of the equation denotes that the adversary acquires location data subsequent to the user at a particular time t, and derives the posterior probability of the user's sensitive position S at a particular time t. And according to our definition 1, the adversary collection of the user location data cannot suppress theta in order for the attackers to deduce the user sensitive location. So therefore, after accumulating the user's position sequence, the difference between the posterior and imperial probability of the user being in a specific sensitive position at a given moment is less than a theta. So at each moment t, the adversary has summarized the summarize equation to summarize the previous knowledge about the user's location. So therefore, the amount of sensitive user data location can expose the attackers in edge node. So I've defined it in definition 1. The privacy preserving techniques that meet data privacy may guarantee the quantity of information included published data in the edge node is less than theta, n theta. So where n is the number of sensitive locations. At any point in this time, users with strict privacy needs may set theta to 0. As a consequence, a user must ensure that the location data they post does not jeopardize their theta privacy in any sensitive location. They only need to adhere to the privacy standard. In our system modeling and analysis, we have these figures at here to demonstrate how does the system works. So this figure illustrates the proposed DDS-DP model utilized in the SDN-enabled edge computing service. So both schemes secure location-aware privacy data between users and edge node. We begin with modified SDN control layer. So this novel control layer attempts to offer a real-time clustering solution. It uses the modified affinity propagation clustering techniques. As the clusters are constantly updated, so attackers cannot identify the source of the first connected edge node. As a result, clustering protected privacy. The clustering will give a first protection of the privacy. And the security level is also increased by modifying the Laplacian mechanism, which is our first scheme. We utilized the QoS mapping to assess the data utility and the privacy protection level. So therefore, the SDN-enabled edge computing service provided the highest privacy level and the data utility protections according to our framework. So in terms of dual approach, so our first approach is the edge node clustering model. We use the edge node clustering to conceal the real position information from user in the first scheme of the entire model. The preservation approach successfully avoids the opponent from quickly invading and allows more complex attack measures. So each cluster is composed of at least 2 or more edge nodes. So instead of direct connections, users are assigned to edge node clusters, then span a large region under the adversary's attacking paradigm. Adversaries need necessary analytical stages as a precise selection gets increasingly difficult. So in our model, the first approach we're doing is to calculate the weight factor and the unification process. The distance-based location is a popular location-aware privacy-preserving techniques in edge computing. So we determine the distance based on the user situation by analyzing the arrival time and its difference between the arrivals. So typically, each edge node calculates the user position via a distance-based location method. If location information is exposed, user privacy will be jeopardized. So moreover, in order to establish the current location of the user, we selected a node must be aware of the location each reference node. If the adversary may perform location spoofing or other attacks against the reference node, if geographical location information for the reference node are reviewed. So we calculated the position distance between a specified edge node and a first node that using our matrix S. And then we developed our cluster triggering process. So in the triggering process, we mainly use the method of EWM, the entropy weight. So that therefore, the first step we're using is the weight factor, and then we calculate the redundancy rate, and we comply to the weight. And then we establish the weight. After we establish the weight factors for each element in each dimension, so the clustering process is performed using the weight factors. And we assume that the trigger, the TTG, is the threshold value for the clustering that is dependent on the edge network distance. And then the outcome of the triggering process and is determined by the weight factor computed for each element. So therefore, the clustering is defined by the edge node factor associated with the maximum value. And then the second step we are considering is the affinity propagation-based clustering approach. So on the basis of modified AP mechanism, we developed a clustering model. The AP is basically a semi-supervised clustering method based on the closest neighbor propagation. So unlike other clustering methods, AP does not need a final number of the cluster to be specified, which is going to be a really good advantage for our edge node clustering. So in edge network, the input data may be various type of as a result of our triggering mechanism, weight factor based selections. As a result, AP method is the optimal choice for grouping edge nodes. So to establish the AP based clustering, first step we consider is the prereference parameter. So the similarity between the clustering center will be defined as a sim IK. And the second step we will do is to evaluate the responsibilities, which indicates the degree to which data point is appropriate for designation as the cluster center for the data point. And then the third step we consider is the availability. After the availability, we consider the damping factor. The damping factor will be used as algorithm repeatedly, which will keep that update the availability and the responsibility value. And after that, the second scheme is focusing on the epsilon customized differential privacy scheme. So each user in edge computing exposes their sensitive location data during connections establishment. However, before this location data is released, it must be protected from the disclosure. We developed the first clustering scheme previously based on the SDN clustering approach, and that enhances the difficulty level when an opponent intends to attack. Additionally, the model secures the released data with a tailored degree of protection based on the cluster distance. And moreover, the second scheme will seek offer to customers, or the clients, the users, with the uttermost inner privacy protection. So to get a greatest protection, we compromise the epsilon customized differential privacy and introduce the Laplacian noise to the cluster. This time to the cluster. So therefore, the first step we're analyzing is the QoS data utility mapping. Since the previous paragraph specified the distance between each cluster as a sim ik, and the softmax function was utilized to describe the QoS data utility function and the privacy protection level epsilon in our DDSDP model. And in a multi-class problem, the softmax function assigns the decimal probability to each class. And moreover, it is often used to visualize the utility of data and the level of privacy protection provided by the QoS. Therefore, we have the first equation of the step 1, which is the QoS data utilities mapping. And then the second step is we adding the Laplacian mechanism and the Laplacian noise. On preserve anonymity of the location, we use probabilities clustering to the initial results of the single clustering query. To protect the user's privacy when it comes to a location-aware information, we utilize the Laplacian techniques to change the actual value by adding the Laplacian noise to the original clustering result data, where it will guarantee the differential privacy both before and after noise addition. Then the third step we consider is the epsilon customizable differential privacy formulation. And to prevent the release in edge nodes, the model epsilon customized differential privacy method, we map the privacy protection level using the clustering method and a multi-hoop with the QoS. Use the subminute-sensitive location data under the edge computing clustering paradigm, and these data must be protected against the attackers. Edge node also vary in capacity and the processing capabilities. As a result, we construct the second scheme with the customizable differential privacy. And at the end, last step we're doing is to try to achieve the optimal trade-off. Therefore, we come up with the step 4 equations, where the optimal trade-off will be evaluated based on the anticipated greatest degree of the privacy protection and the lowest data usefulness. And let's step into our performance evaluation. So we basically first assess the data utilities by sampling the time periods at the various places, and then the privacy protection levels at different locations will be also analyzed. And the experiment assess the cluster approach performance, including clustering, transmission, and loading outcomes for the total edge nodes. So in this time, the datasets we're using is WIC free Wi-Fi access points location dataset. This is the dataset from Australia government, and representing 517 nodes with over 300 kilometers in distance, and with minimum 250 megabytes data per node per day. And we will compare our model with the CDP and the CCDP, where the CDP is the classic epsilon differential privacy, and the CCDP is the classic customizable differential privacy. So in the first approach we've conducted is the clustering capabilities, where we achieved the first scheme. The clustering system will produce the excellent clustering results, where we have a total number cluster of 16, plus some individual node as an individual cluster. And then the second one we analyzed is the data utilities performance with 3 different epsilon values, and also the different locations privacy levels with 3 different epsilon values as well. So in figure 3, it will illustrate the outcomes of our DDSDP model data utilities, and that figure displays the overall QoS functionality. We compare our findings with the raw data values between epsilon equals 1, 0.5, and 0.1, and 0.1. And the third performance evaluation we have done is the performance against attacking scenarios, and that demonstrated the performance level of the privacy protection in the wormhole attack scenario against the solitary and a cluster node, a clustered edge node. As a result, DDSDP can offer stronger protection strategies when assaults occur where CDP and CCDP suffered. And in conclusion, we proposed a dual scheme privacy structure, and the extensive experiment finding established that the proposed model and the clustering approach not only exhibit high reliability in specific situations, but also offer configurable outstanding performance. And furthermore, for the future work, we will consider about the Markov decision process within a multi-stage game in order to continue to enhance our performance evaluation. That's all for the presentation. Thanks for listening, and any questions are welcomed. Thank you so much.